this is J. Sravana, working as Assistant Professor in AC Department in Institute of Aeronautical Engineering. Our today's topic in microprocessor and microcontroller is physical memory organization and general bus operation. So, in our 8086 architecture, we use the concept of memory segmentation. So, what is a memory segmentation? Segments are nothing but we have divided into some blocks. So, the memory which you are having, that is nothing but how much memory is available in 8086 is 2 power 20. 2 power 20 is nothing but 20 indicates those are address lines. So 2 power 20 gives you 1 MB memory. This 1 MB memory is utilized by the microprocessor in order to function all the operation in 8086. So in order to make a convenient way and in order to make it as a faster operation, we have divided the memory 1 MB memory. So we have a 1 MB memory capacity which is divided into 16 logical segments. Each segment is 64 kilobytes of memory. So how the address is defined to this logical segments are, it is a 20-bit address. So as we have 8086 is having a 20 address lines, so the memory which is segmented indicates by 20-bit address. So we can always, in order to access our 8086 microprocessor, uh, from our 1 MB memory, we are accessing via an address which the address will be of 20 bit. So this 20 bit will start from the memory address location of 000000 to FFFFFH. So the starting of the memory location is from 0000H to FFFFH. So this memory is divided into a logical segments, 16 logical segments. As we said, each will pursue a different usage. That is nothing but you are dividing the microprocessor memory is divided into different segments. The segment, what is the usage of the segment in order to access the data in a faster way? How you can access the data in a faster way is our memory, depending upon the application or depending upon the user, the data which I need to access, the data is saved in a particular memory location. So where you can access the data directly. So suppose I have a data of my college of first year, second year and third year. What I can do is I can store my data in the segment wise. Segment wise is nothing but blocks. Here first year data I have stored the first year data, and in the second block I have stored the second year data, and third block I have stored the third year data. So this data year wise which I have stored for particular department, I can access the data if I want the student data of first year. My memory location directly point out to the first memory location. If I want the third year student data, my memory location directly point out the third block. So that is what the faster operation is done by the segmentation. Depending upon the usage, you have divided in the memory into segments in order to access at faster rate. So you can divide this into a code segment, and we have divided into data segment, extra segment and stack segments of each of 64 kilobytes. So we have divided this data. This is overall of 1 MB memory, and this 1 MB memory, each memory location is of 64 kilobytes. And so like that we have 16 logical segment, 1 to 16 logical segments. Each will serve a different usage according to the user what he have been. So generally we have code segment which stores the code of the particular application. Suppose I have written a code for any external device for printer, suppose. So the printer related code data, the code either have written in an embedded C or assembly language code, that code is directly served in the code segment. And data segment, what is a data segment? In the data segment, if I am going for any data processing, like I'll go for simple addition and subtraction operation. In addition subtraction operation, I am given a data in kind of string. So the string of data should be stored in some memory location where I can take my data. So that is present in the data segment. Extra segment, extra data is nothing but apart from the data which you are processing. If you have more operations, more data in order to access, if our memory, the data segment which is not sufficient, you can go for extra data. And the stack segment, and stack segment are related to the stack operation. So stack operation, we know we are going for simple first in first out operation, last in first of operations. So the instructions which you are using for stack segment are push and pop. So this the all the memory references are made relative to the base address contained in high speed segment. So how these segments are functioned, how you can access the segment which is given. So we can access the memory or the segment, you can say, by using an address. So here this logical 16 logical segment can be accessed by using the base address. This is a base address which consists of high speed segment, which is given to the high speed segment. Those are the 16 logical segments. And the segment types were chosen depending upon the addressing needs of the program. So how the address, how you can address the memory location depending upon the addressing modes which you are assigned to it. You can address the memory location, you can access the data, and these accessing data can be always these logical segment can be always accessed by the base address. Next, all the information in one segment type shared the same logical attributes. So either you can go for a code or either you can go for data. By structuring the memory into reallocated areas of similar characteristics and by automatically selecting the segment registers, programs are shorter, faster, and more structured. So we have already predefined our programs into the particular memory locations. This makes the CPU more faster in order to access the data. Next, how the data can be accessed, how the data operates. Suppose if I need to access the word operands, word are nothing but a 16 bit. If I need to access a 16 bit, my memory can be generally can be divided into even or odd address boundaries. So thus it consists of even kind of data and even odd kind of data. What is the even kind of data? What even kind of data is nothing but the memory locations which are having even addresses are separated in a separate memory location, and odd type of data, odd type of addresses are occupied for the separate memory location. So for the address and data operands, the least significant byte of word is stored in the lower value address location, and most significant bit is stored in the higher address location. So we know the data which you are giving will consist of a lower byte as well as higher byte. So lower byte indicates, so overall overall, the lower byte plus a higher byte indicates a word, but accessing the data when it comes into consideration, you need to access first a lower byte of data, next higher byte of data. So this lower byte of data is addressed in the lower value address location, and higher value is given in the next higher address locations. So the bus interface unit automatically performs the proper number of memory access, one of the word operand in the even byte boundary, and two if it is in the odd byte of boundary. So except for the performance penalty, the doubled access is transparent to the software. So you are dividing our memory, one in the physical cases and another in the logical cases. So in physical cases, you are dividing our memory into a even bank and odd bank. And in a logical case, you are dividing the memory into number of segments. So here depending upon the performance, if I need to access a data which is present in a memory, so what I need to do, I need to fetch the data and decode the data and then execute the data. So here fetching does not requires any time in the memory segmentation. So it only depends upon the decoding and accessing. So the performance penalty does not occur for the instruction fetches, only word operands which you are decoding it and which you are executing it. And the physical memory is organized in higher bank of, you can say, D8 to D15, and a lower bank of D0 to D7 of 512 kilobytes. So how much the memory bank is divided into even and odd is 512 kilobytes, addressed in a parallel by the processor address of A1 to A19. So the even and odd bank address which you have divided can be accessed by the address lines in A1 to A19, and A1 indicates that whether you are using a lower type of data bus or higher byte of data bus. So actually how many address lines we have? 20 address lines. The 20 address lines we are starting from A0 to A19. So in order to access the memory banks, A0 is assigned only in order to access either the lower kind of data or upper of the data. That is nothing but lower means D0 to D7 and upper means D8 to D50. And separately A0 is assigned, and remaining which starting from A1 to A19 are used to access the data from the even bank and from the odd bank. And the processor provides two enable signals. The enable signals are BHE and A0 to selectively allow reading or writing either in an even bank or either in the odd bank or both. So separate signals we have: bus high enable signal and A0 signal. Bus high enable signal ensures which data can be placed on the bus, either a lower data, that is nothing but D0 to D7, or either the higher data D8 to D9. And A0 indicates that which need to access, whether the data from the even or whether the data from the odd. And the instruction stream is fetched from the memory, has a word, and it addressed internally by the processor to byte level as necessary. The instruction how it is fetched are in terms of words. Here you can see the memory references and the segment register used and the segment selection rule. So how the data is taken. So here you are seeing you have an instruction. So for instructions for the code segment, we are using a code segment which is denoted as CS. Automatically with all the instructions are prefetched. So depending upon the segment, how the instructions are taken is defined in this table. So in stack segment, all the stack pushes and pops the data which you have taken, and the memory references are related to the base pointer, base register, except the data references. So how, depending upon the base register, we are accessing the data, whether you are pushing the data with the particular base address or whether you are popping the data with that particular address. And local data is nothing but DS, you can say. The data referred with relative to stack or destination of string operation or explicitly overridden. So all the data transferring kind of instruction like string operations, if you go for, all the data is given in the local data segment, that is DS. Next one is external global data. External global data, you can define it as an extra segment. So explicitly it can be given to the extra operations which you are going for, like string operations, destination of the string operations. And here, this is a actual memory organization which is divided. Here, this is a physical memory organization, and this is a logical memory organization. What is a physical memory? As we have said, for our 8086 microprocessor, it is divided into even bank and odd bank. So even type of bank can access the data from odd bank can access from D18 to D15, and even bank will access from D0 to D7. So D0 to D7, it is indicated as lower byte of data, and this can be taken as a higher byte of data in the physical memory organization whenever you're going for. So it is indicated as memory 1 and memory 2 in order to determine which data should be present on the bus, can be indicated as A0. If A0 is equal to 0, it means that you are going for odd bank of address, that is D8 to D15. If it is 1, then you are going for D0 to D7 on the address bus. So always make sure bus high enable is made bar is taken, BHE bar. BHE bar indicates whenever it is equal to 0, then only it works. So you can access, R80 can access the data in an even bank by using an even bank, and odd bank, where even bank is from D0 to D7 and odd bank is from D8 to D15, and this can be taken by using the A0 and BHE pins. And next you comes under a logical segmentation. So logical segmentation, you can see this is one segment, this is one segment. So here each segment was having some code address. So each segment is denoted with an address which gives you the base address. So this is a starting address of the segment 1, and this is an ending address. So here you are denoting first the base address, that is nothing but 1000, and this segment will have the starting address of 000 and it will end with FFF. And if you see the second segment address, the CS address, a code segment address is nothing but from 2500 is a starting address of that segment, and the internal memory location which is starting is from 000 to FFF. So this indicates the offset address of the segment, and this is a starting address. So you can see this is a segment where this segment will have a code segment address of 2500, and internally the memory is starting from 00 to FFFF. So this starting address, the instruction pointer will start from 00. So always, if I'm giving a address to the segment, and in that segment you are again having the starting address and ending address in which you are working. So see here, this is a how so this memory, logical memory which you have taken, can be always assigned with 20-bit address. So this 20-bit address, how you can access this 20-bit addresses by using the physical address generation. So what is a physical address generation? Here, each segment internally is accessed with the 16-bit. So the memory or the address which is denoting will be a 16-bit, but our memory, the logical segment, the segmented memory address is denoted by 20-bit. How the 20-bit address is denoted? Suppose this is a segment, I'm having. In this segment I have a code segment address which is of 16-bit, and the segment starting address is starting from 000, and it is ending from FFF. Okay, so here this will be the instruction pointer where my segment will start accessing from the starting address. That address is called as an instruction pointer address, and the code segment starting address is the segment CS, this, which is another 16-bit. So what I need to do, my CS is actually a 16-bit, and my this is CS which is 16-bit is a segment address which you are denoting, and the instruction pointer is nothing but it's a 16-bit which you are working in that segment, working in the segment, which this is an instruction pointer always indicates in which memory location you are accessing. So here both are CS is a 16-bit and instruction pointer is a 16-bit, but my memory, the memory which I am having, 1 MB memory, is denoted by 20-bit. So how can I access, my processor can access the address of address which is denoted for the memory, not the individually, not the individual address bit which I have assigned. So my memory overall, it shows a 20-bit address, means my 20-bit address should carry the 16-bit data which I have given. So how I am given, have given in the logical segments. So I need to know which logical segment I'm using. Either I'm using the code segment, or either I'm going for stack segment, or either I'm going for extra segment. That segment address I need to know, which is a 16-bit. And another point is, in the segment address, in that segment address, which memory location I'm executing, that is denoted by the instruction pointer. So here the starting code segment address is 348A. So this code segment, which is a 16 segment, my code segment is having, suppose, 348A. 348A is a 16-bit address. This is a code segment address. Suppose I'm working in a code segment, that code segment address is denoted by 348A. And in that segment, in which memory location I'm accessing is 4214. Right. So this is also a 16-bit. So how can I generate a 20-bit addresses? I'm including extra 4 bits in my LSB of code segment address. Code segment address is having a 16-bit, and that 16-bit I'm adding another 4 bits in the LSB. And this then you will generate how many bit is 20-bit. This 20-bit is added to the instruction pointer, which is of 16-bit, and this gives you a 20-bit address. So here we have seen an example here. So this example will give you how a 20-bit address have been generated. So start code segment address is 348A0. So this 0 bit indicates that we have added 4 bits to CS to generate 20-bit, right? So that is what this is, a 20-bit address, and this 20-bit address is added with the instruction pointer address. Instruction pointer is in which memory location you are accessing in the code segment, which is having a code segment address is 348A0. So this memory location will be added, and you will this instruction pointer address is 16-bit, which is 4214H, and this is added with the CS, and you are generating the 20-bit address, that is 38AB4H, right? So this is actual. So this 38AB4 is nothing but 20-bit, which is having in between the range of 0000H and FFFFH. So this is how. So our memory organization in the physical type, you are divided into even banks and odd banks, and in the logical way, you are dividing into a logical segments, 16 logical segment, each of 64 kilobytes. Right, so we can access the physical memory organization, which is divided into banks, by using A0 and BHE pins, which are connected to the even bank and odd bank, which can access 0 to 7 data, lower byte, and higher byte of D8 to D15. Whereas logical segment, you can access the data from the logical segment either by using a code segment, or either you can use a data segment or extra segment. By taking the data, you need to generate a physical address which is of 20-bit. So what you need to do is, first you need to generate a segment address of 20-bit by adding the LSB to it, LSB of 4 bits to it. Then the code segment address will be generated with the 20-bit address, and that 20-bit address you are adding to the instruction pointer of the code segment which you are working, which is a 16-bit. So when the 20-bit of code segment is added with the 16-bit of instruction pointer, you will generate a 20-bit address. So that 20-bit address is a physical address where it is shown in the shown for the memory of 1 MB. So this is what a memory organization of 8086. So here, and we have another a reversed memory location. What is a reversed memory location? So certain locations in the memory are reserved for a specific CPU operation. So as we are as we have specified, we have reserved, we have blocked that memory to particular application. Like data segment is accessing only data, and code segment is accessing only code. So you have fixed that memory location with some particular data, where whenever you want, you need to store that kind of data only. So like that, we have a reserved memory location. So these reserved memory locations are from FFFF0H through FFFH, are reserved for operations including jump to the initial program loading routine. So these memory locations are only specified for the branching instructions. So branching and looping instructions means we need to operate from one memory location to another memory location, or if I need to operate the iterations, number of iterations, we can use this specified memory locations, that is FFFF0 to FFFFF. And the following reset, the CPU will always begin the execution at the location from FFFF0 where the jump must be. So suppose I need to use this reserved memory location. What I need to give is, whenever my CPU is gone to reset mode, my address location will begin from FFFF0, where and locations from 000 through 00 are reserved for interrupt locations. And the memories, that is nothing but 00000h and uh, 003FFH are reserved for the interrupt operation. And each of the 256 interrupt types has its service routine pointed to a 4 byte pointer element consisting of 16-bit segment address and 16-bit offset address. So as we know, we have 256 software interrupts for our 8086. These 256 interrupts have an interrupt service routine pointer, where that pointer will have a 4 byte. It stores the 4 byte, which consists of 16 bit of segment address and 16 bit of offset address. And the pointer elements are assumed to have been stored at respective places in the reserved memory prior to the occurrence of the interrupt. So depending upon the priority occurrences which I have given, it need to store the content or the data or the information only in the reserved memory location which is assigned to it. So see here, this is a reserved memory location where you can see the 0h to 3h. It denotes the interrupt pointer for type 0. And next, from 4h to 7h, you have denoted with the interrupt pointer for type 1. And so like that, how many interrupts you have is, you have interrupts 256 interrupt. So here from the 256 interrupts from type 1 to 255, the memory location is accessed from 3FFH, and which is starting from 7F to 3FFH. And remaining, if you go for jump instructions, as we have seen for looping and branching jump instruction, you can use this memory location, that is FFFF0 to FFFFH. So our memory locations which you are having a reserved are given to 256 interrupts, and other memory locations are for jump programming. Jump programming instructions. So jump program instruction will start from FFFF0H to FFFFH, and interrupts 256 interrupts are reserved for the memory location will start from 0H to 3FFH. So this is actually reserved memory location which is assigned. So now this was the memory which you have taken. How the memory is organized. And next we'll go for general bus operation. So in general bus operation, how the operation can be done. So how you can take the data from the memory to the processor. You can take the data from the memory to the processor via an address lines and data lines. So 8086 has a combined address and data bus, commonly referred to time multiplexed address and data. So as we know, we have multiplexed the address and data, that is nothing but AD0 to AD50. Alright. So the main reason behind the multiplexing of address and data bus are in order to reduce the number of pins in the by defining the dual inline package, which gives you a 40 pin IC. So separately, if you define the pins for address and data, what is happening is each pins occupy more power in order to function. So for one pin I need to function. It may be a data or address or any sort of pins in 8086. I need to apply a voltage that is nothing but equal to 1. The pin will be equal to set, and then the function starts operating. For the particular pin function starts operating. Like that, if you are having more number of pins, so all pins you need to function at any of the time. So any of the time that pin will be equal to high. So what is happening whenever you are going for address and data bus, which we have used, the address and data bus separately, all the pins will be equal to high. That is nothing but 16 data lines will be high, all the 16 pins will be equal to high, and all the address of 20 bus will be equal to high. So what is happening, the power consumption is becoming more for that pin. So what happens when the power consumption is more for an IC? It will burst out, or the IC doesn't work in. So in order to make all these considerations, we have multiplexed our address and data pins in order to reduce it into 40 pins by using a dual inline package. So here, now what we have understood is only one single bus is present which act as both address and date. This is what the indicates. Now, basically, the processor bus cycle consists of 4 clock pulses, and they are T1, T2, T3, T3, and T4. The address is transmitted by the processor during T1, and remaining bus will be enabled depending upon the pins used, and according to that, the data is occupied. So, a single bus you need to access either for data and either for processing either data or either in order to process the status. So how it is processed? See here, this is a general bus operation. In this general bus operation, how the data can be taken from the bus, that is multiplexed address and data bus. In that multiplexed address and data bus, I need to send the data and receive the data. Means memory need to read the data and memory need to write the data. How this read is performed, how this write is performed, let us see. So for a single, if I am giving a instruction, move AX comma hash 2222. So what is happening to the this instruction? I need to read, and I need to read means I need to fetch, I need to decode, I need to execute. What I need to do? I need to read, or read the data, that is fetching, and I need to execute that. And after that, I need to write the data, the resultant I need to write. So that is what the read and write operations of the memory. So first we'll see the read cycle. In the read cycle, for one instruction, in order to read, how many clock pulses are required is 4 clock pulses. In that 4 clock pulses, T1, T2, and T3, after 3, the wait time is included, because if any of the processor is slow, then what you can do is you can wait the data. Means if there is no synchronization between the device, external device to the processor, I need to wait for some time in order to make the synchronization. So a wait signal is included, and then a T4 time period is included. So see here, first I need to process the data. In order to process the data, how can I process? First I need to know the address. So address will be enabled at the first time period, and remaining time periods the address will be low. Why? Because at first, once the data is once the address we know, from the address we'll take the data. So first clock pulses is enough in order to take the data. So first ALE will be equal to high, and uh, next uh, next pin which is included is S0 to S2. S0 to and S2 are status pins, which these pins will give you either you are working with the read operation or lower byte of data or higher byte of data. So you are making this as low for T3 time period. After getting the data, then you need to go for the accessing of the status, whether you need to go for lower byte of data or higher. So first three time periods, you can see the status pins will be equal to low. Bar pins means bar indicates that whenever it is low, then only it can access. A means those are active low. So S0 to S3, these are low when you are getting when the address is enabled. When the address is enabled, my processor need to know how many bit of data I need to access. That is what this pin is low at till T3 time period. Next, address and status bus. Address and status bus indicates first time period address is initialized, that is the A16 to A19, and next the status will be initialized. So why first address is enabled? Because here if you see, address is enabled till which time period? T1 time period. So till T1 time period, what all the pins which are related to addresses will be equal to high. So address and data, address and status pins, address and data pins. If you see here, starting time period when the address is enabled, at that time period only you can see the address is available on it. So that is address and status, but that is nothing but A16 to A19 is enabled at first time period, and address and data here is enabled, that is nothing but A0 to A15, first address is enabled. When the address pin is equal to low, then what is happening? The remaining, which is another pins which have multiplex, will come into consideration. Here address and status pins, address pins are multiplexed with the status pins. So initially we have latched the address, we have taken out the address by making ALE high. Next, ALE I have made low. When ALE has made as low, then address pins will does not work. You need to make the remaining multiplex pins, that is nothing the status pins. So see here, first till ALE is high, address is enabled, and for the remaining clock pulses, the status pins are enabled. Similarly, address and data pins, if you check, the address pins are high for T1 time period, and when the the address latch enable pin is low, here the data bus is enabled, and from the address you can take the data. So example is, you are going for some particular you are searching for a particular person, means which is having which he is a topper in the college. So how you know he is a topper in the college? By knowing the name. By knowing the name, you are getting the data of the particular person with the full marks. So the name of the person is an address, right? And the marks which you are getting is called as a data. So first we need to know the name, then only you can know the data. So first you need to get the address, then only you can get the data from it. So this is what is happening in the address and data multiplex. And next, that is what you are making initially ALE as high. Next, read and write, read interrupt. So read is nothing but whenever you have a data, then only you can read it. So that is what initially this pin is high. Read bar indicates that whenever it is low, then only it can access. So initially it is high. There is no requirement of address now for us. Why? Because address cannot be read, only data can be read. So till here, the data, the read bar pin is equal to high. And then read bar pin have made us low for the next clock pulses when the data is present in the remaining clock pulses. So what happened? We have a data at this clock pulses. When you have data, then only you can read the data. So at this time period where the data is read in the T2 time period, T3 and TW time period, the pin will be equal to low. This means the read operation is done here. And next, ready. Ready is nothing but whether you need to send the data. You need to know whether you need to wait the processor for some time, or you need to you need to send the data. So read is nothing but will be low. It indicates you are waiting for some time. When it is equal to high, you are ready. The data is present on the data bus, and you can, and it is also present in the read pin. Read pin is enabled, so you can send the data. It is ready. So this pin will be equal to high when the read pin is equal to high. And D by T bar. D by T bar indicates that uh, DT by R bar. DT by R bar means what? Data transmit and receive. So data receive is a low. It works only when it is an active low pin. Means whenever it is equal to 0, then only it works. And data transmit. Data transmit is equal to 1. Whenever it is equal to 1, then only this will work. Transmission will work. So if you have a data, now if you have a data, I need to read. Read means what? I need to transmit the data. Then transmit the data indicates that and read operation indicates that you are receiving the data. That is nothing but dt by r bar pin whenever it is equal to 0. Read operation is done, means you are receiving the data. And whenever it is equal to 1, transmission is done. So dt by r bar is made as low. It means that you are reading the data, means you are receiving the data. Right? Means receiving means reading. Transmitting means writing. And data enable. Data is enable. Data enable bar. Bar indicates that whenever it's an active low pin. Whenever it is equal to 0, then only you can access it. So whenever it is equal to 0, it means that you are accessing the data. So see here, it is low when the data transmission pin is equal to low. And write. And write is, it's nothing but write bar. Whenever you are going for reading operation, writing operation is not used. So that is what it is mean as high. W bar. Bar, whenever you are having a bar for any of the pins, those are active low. So whenever it is equal to 0 only, it will work. So here I am doing a reading operation. So what is the use of write operation? So that is what does an active low. So I have made this as high. For writing cycle, you will make as low. So similarly, how the reading operation is done, you can also do writing operation. So what is the writing operation means? Transmitting. So here the same. Initially at T1 time period, you are enabling the address ALE, address latch enable. Next remaining are low. And next, after address pin is enabled, next you need to vote for the status. So status should be low. That why? Because those are active low. How many bits of data, whether I need to go for lower order, higher order bits of data, I need to know that. So that is what this is made as low initially. And next, what are the multiplexed address and data pins? We have address and status, address and data. So in order to take the data from this address, multiplexed address and data lines, we need to initialize, we need to make high whenever the ALE is high. So address and status pins, address are latched initially, and next when ALE is low, status are latched. Similarly for address and data bins, database. For address and data bins, initially the address is latched till ALE is high, and when ALE is low, the data is latched. Next, read pin. Read pin is not required for the write operation, so it is active high for overall. And ready pin. Ready pin, unless and until you have a data, then you can't go for transmission, whether read operation or write operation. So here, when the data is present, then only the pin is equal to low. Next, dt by r bar. Dt by r bar, as we have said, whenever we need to read operation means you're going for receiving. Whenever you're transmitting means it means you're writing. So it is made as high. Dt by r bar, it is not an active low pin, so this will be equal to high when the data is present. And data enable. Data enable is an active low pin. It means whenever it is low, the data is present. So this is a low for this time period. And next, write operation. Write operation is also an active low pin. So this will be low only when the data is present on the dt by r bar, and only when the time periods data enable are low. So this timing diagram, this is an overall timing diagram, how the bus operation is done for each time period, how the pins are made. At means it is made as high or it is made as low. This is indicated by this timing diagram. So a simple bus operation can be understood by this timing diagram. So this timing diagram shows you at what time period. So how many clock pulses required for one read and write operation is 5. That includes T1, T2, T3 and a wait signal with the T4. Wait indicates that if any of the processor is not synchronized in the proper way, we need to wait. So that is what a TW is included. So here these two operations are shows you the operation, how the data is transmitted and how the data is received, and the pins which are activated when the data bus operation is done. So what are the pins which are activated is clock, ALE, S0 to S2 bar, address and status, address and data, RD by INTA, read, DT by R bar, data enabled, and write or read. So these are the pins which are activated. At what time period the pin is equal to high, at what time period the pin is equal to low, we have seen in this timing diagram. So as as we have understood what is how the bus operation is done and how the memory is divided into a physical allocations, even and odd, and how the data is divided into logical way by using a logical segments. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.